Welcome to Bridge the Gap, the physics-oriented podcast of the TU Graz,
where we give insight into physical topics and the life of scientists.
Hey Daniel, what do you know about black body radiation?
Absolutely nothing.
Absolutely nothing, so you're saying that there's a black spot in your knowledge?
Well, one may phrase it like that.
Okay, but I mean, jokes apart, black body radiation is crucial to quantum mechanics, and since today we're going to talk about some of these most unintuitive aspects of quantum mechanics, I thought it was worth mentioning it.
Very nice. And I think we're also talking about particle-wave duality and the uncertainty principle, is that right?
Oh my god, you read my mind. So yeah, I mean, there's also one famous joke related to this uncertainty principle. Are you aware of it?
No, I'm not, but I would be very curious to hear it.
Really? Okay, so the uncertainty principle was attributed to Heisenberg, so the joke goes as follows. Heisenberg gets pulled over by a cop who asks him if he knew how fast he was driving. And he says, "No, sir, but I knew exactly where I was." I mean, this relates to the impossibility of measuring velocity and position at the same time for the quantum particle. But never mind, we'll talk about this and other aspects.
Okay. Well, we were wondering what some of our students and friends know about today's topics, and here are some of their answers.
Very curious to hear them.
I think there was the need to go beyond classical physics because of experiments told us that there should be more.
So what I know about quantum mechanics is mainly from my quantum mechanics lecture last year, where we learned about different operators and potentials and so much more. And there was a need to go beyond the classical physics model because it just didn't hold up anymore for the smaller particles. So quantum mechanics was invented to explain them.
I don't know much about quantum physics or anything at all. And my guess that there was a need to go beyond classical physics because without going beyond what we know right now, there is no progress, there is no discovery.
Quantum mechanics is one of the most well-established theories we have to address reality and try to describe it. But sometimes people have the impression that it doesn't make sense at all. So today with us to discuss about this topic, Markus Aichhorn, professor at Graz University of Technology. Markus, hi.
Hello.
First question for you. What is quantum physics and why was there even the need for going beyond classical physics?
Okay, so quantum physics, if you want to have a definition of what it is the physics of microscopic phenomena. So phenomena or properties of matter, properties of the universe that live at very short length scales and possibly also very short time scales. Yeah, that's also why it's very difficult to grasp for people. We are talking about length scales that are nanometers, even shorter, even smaller. So it's nothing that you can see. It's nothing that you can feel. It's nothing that you can hear. It's hidden in the structure of what surrounds us without being able to grasp it. Yeah, so that's the problem with quantum mechanics. Now, why was there a need for this theory? We can go back in history a bit. There was the golden era of physics in the 19th century even. Yeah, so before quantum mechanics was developed. So that was the time of Maxwell, Faraday, Ampere. So they did all this beautiful electrodynamics development. So they understood how electromagnetic waves work. They got to know how thermodynamics work. So they had an idea of what is energy, what is heat. Classical mechanics was there. So we could calculate, or they could calculate at the time, how particles move when they are exerted to some external forces. And then there was even a saying that at the end of the 19th century, physics is done. Yeah. So we know everything, all the theory is there. So what happens in the future is just a minor tweaking of all these equations, but we understand everything, yeah? And then came the time of 1900 roughly, maybe a little bit before, starting 1880 or so, when there were a few experiments that could not be reconciled with these theories. Yeah, it was not just tweaking formulas a bit, but there was some fundamental problem with these experiments. And one of them was, maybe the most famous one, is the black body radiation. Yeah, this has been known since many, many years that pieces of matter, they emit radiation. Yeah. And it was characterized with a great extent in experiments for different temperature, different materials, different geometries, and so on. So one had a very good idea of how this radiation and the radiation spectrum, that means at which frequency is what amount of radiation coming out. This has been known for a long time. Yeah. Now people tried to solve this in classical theory, which worked nicely at very low frequencies, meaning at very low energy that is emitted. But for very high frequencies, this failed dramatically. Yeah. So that was the famous Rayleigh-Jeans assumption, I think, yeah, which we nowadays call ultraviolet catastrophe. Yeah. Ultraviolet means high frequencies, high energy, and there the thing just didn't work. Yeah.
So it means basically that the black body would emit forever, or that you can have like an emitted energy which is infinite.
Yes,
that was
exactly. If you push this to the limit and do not introduce some ad hoc cutoff that you would need to do, then it would mean this body emits an infinite amount of radiation every time you look at it. Yeah. So, and it has been known from thermodynamics that energy is a conserved quantity. By the way, this is not something that we invented centuries ago, but it was also in the 19th century. That was Clausius, Clapeyron, and all these people. So all these concepts are newer than we think sometimes, yeah. But we know that energy is conserved, so it cannot be infinite. Where should it come from? Yeah. So that was the problem. And how could that be solved? That was the glorious idea of Planck, let's call it like that. So he got the experimental results, and here one has to say that all this is a bit more involved than it's presented nowadays, because the idea of what we call now quantization has not been invented by Planck. Yeah, the idea that things that surround us have some minimal amount or some minimal unit. This is even going back to the ancient Greek, right? It was Demokrit with the atomos. So the atom as an unbreakable quantity that is the smallest in the universe. It's from 2,500 years ago or so. And then even Boltzmann, now bring in Boltzmann, we are in Graz, so it's a very famous physicist working a lot in Graz. He also had some ideas about quantization. He didn't call it like that, but in some of his letters you can see sentences like, yeah, there should be something with the energy not being continuous, but without foundation, without calculation. So it was all very shakily formulated, but these ideas were there somehow. And then Planck said, okay, let's use this and assume that energy can just be there in finite units. He didn't call it quanta. Yeah, that came later. He just said, we need finite units. And if we assume that this is the case, we can solve these equations and we get the spectrum that is perfectly on top of the experiment. Yeah. So that was the solution at the time. That was 1900. By the way, at that point, Boltzmann was a very famous physicist, and Planck sent his first draft of this work to Boltzmann, saying, okay, what do you think about this? And Boltzmann said, yeah, it's nice. He didn't say much more because it was at the end of his life, but he said, okay, good. And Planck published that, and that was the first, so to say, invention of this energy quantization that was used in formulas, so to say, yeah.
So Planck did not realize sort of that it was quantum mechanics that he had discovered. So when did this come? When was the realization that there is something fundamentally new, sort of?
Okay, yeah, that's true. Planck didn't even think that what he did has some physical relevance. Yeah. So when you read his conversations also with other physicists, he called it a sheer act of desperation that he did. So it was just a mathematical construction that he needed to use to get the formula that is what he wanted. And he always thought, at least in the beginning, that this is just mathematically helpful, but that this concept of energy quantization is not real. This is not what the universe is. It's just we need to do it to get the formula, but it's not what we have. Now, the radical new idea that this is real, that this is really coming from the properties of the universe, of the constituents, is by Einstein, actually. That was the photoelectric effect. Yeah. So it was 1905. in this Annus Mirabilis of Einstein, where he did also special relativity and Brownian motion and all the other things. So he said, I have an explanation for the cathode rays. That was the name at the time. So Kathodenstrahlung. Yeah. So people were shining light on a material, and then there was some stuff coming out, and they called it cathode rays. And a long time they didn't know that it's electrons. At some point, people realized it's electrons that come out. And also before Einstein did this explanation, it was well characterized experimentally that there's some problem with the maximum amount of energy that these electrons have, and it's not related to the intensity of the beam, and how can this work with electrodynamics? That was another very famous experiment that failed in classical physics, or the explanations of classical physics failed for this experiment. Now Einstein said, okay, I take this idea of Planck, but I say it's real. That was what Einstein basically did. He said, energy is a quantized property. It cannot be cut into smaller pieces than that, and it's real. And it's regarded as one of the most revolutionary sentences written in the 20th century, thinking back in physics, because this idea was just so new and so radical that people had problems to accept it. Yeah? With Planck, it was this mathematical model. Yeah, fine. But Einstein now said, no, there's a photon. It's really this one thing that has an amount of energy. It's living in one piece of space. It's there. You cannot cut it. That's the minimal unit. That's it. Yeah. And that was radical new. I think that was, for me, the birthday of quantum mechanics without the formalism, I would say, because the formalism came later. But the idea that this quantum, also Einstein didn't call it quantum. So quantum was invented at the Niels Bohr Institute in the 20s by Heisenberg, where was there, Bohr, Wien, Pauli, all these people that worked then on the modern quantum mechanics, so to say. But at that time, it was all very shaky, and, people tried to just come up with ideas that can explain these things. So 1905, for me, was the invention of the idea of quantum mechanics. Yeah.
It is also quite peculiar that it was Einstein who brought it up, like in a sense, to light, because he was said to be against quantum mechanics. I can still remember, like when I was a student, his famous debates between him and Born or something. Like, so it's kind of counterintuitive in a sense. So like people were just trying to piece together like the information that they had at the time in order to make sense out of it, but without even thinking maybe we're inventing something else. So this is quite interesting.
You're right. The point is that Einstein, he invented the photon, if you want. But what Einstein did not believe is that quantum mechanics is the last theory. Yeah. So in that sense, he said quantum mechanics is fine in the sense we have a mathematical description of nature. We get some results. These results can explain our experiments. But what Einstein did not believe is that the probabilistic nature of quantum mechanics, which is also a very decisive thing. So it's that thing that makes it different from a classical treatment. You can put it like this. He did not believe that this is the final truth. Yeah. So Einstein was, until the end of his life, he was always seeking for this one theory covering everything. I don't know what he called it then, but he was looking for this
theory of everything.
The theory of everything, yeah, that's right. That was his final goal, and he spent the last decades of his life on it, but he realized his math is not good enough somehow, so he couldn't finish this. Yeah, but his idea was that since quantum mechanics is so special, and in particular quantum mechanics has nothing to do with relativity and with gravitation, it cannot be the final answer. Yeah, that was the problem of Einstein. Einstein did not criticize that there is something like quantization. Yeah. There were other people criticizing this, yeah, like Mach in the beginning. That goes back to a very old debate about atoms in general. That was done with Boltzmann and his colleagues. At this time, like mid to end 19th century, statistical mechanics was invented. That was the revolution before the quantum mechanical revolution. We forget about this, that statistical mechanics is just 20 or 30 years older than quantum mechanics. Yeah? And the idea that we have atoms and atoms define what we are and what we do, that was radical new in the 19th century. Yeah? So everything was a continuous description of matter, of waves, of materials, and it was not needed until the time. And only Boltzmann and his colleagues like Gibbs, these foundation fathers of statistical mechanics, they brought in this atomistic point of view. Yeah, and this continued then into quantum mechanics. So these original ideas of having finite units, that was not invented out of the blue at 1900 by Planck. Yeah. There was yet another problem, an experimental problem that we should talk about, that is the properties of spectra of atoms or gases. Yeah, this was also something that has been measured, and I think the original, was it iodide 2 or some molecular gas, you shine light on it and you see that you have a continuous spectrum, some absorption spectrum, plus very defined lines, right? Nowadays we understand what it is. This is just the absorption line of the atomic properties of the ingredients. So it's well defined by quantum mechanics, we know now. And also that was just done experimentally. You might have heard of the Balmer series. The Balmer series describes the energy levels of the hydrogen atom. The Balmer series was introduced much before quantum mechanics. It was Balmer who measured that and found out that the distance between the energies goes like 1 over some integer, just by looking at the numbers, and had no explanation for that. Yeah, and this was another big problem. How can we explain this? The atom, which was invented kind of a few decades back, how can we describe this emission with some framework that gives us really a closed description of it? And that led to all kinds of approximations and all kinds of ideas. Like the first was Rutherford saying, okay, there's a nucleus and electrons just like in a solar system surrounding the nucleus. The existence of the nucleus was also established experimentally. There was this experiment with the gold foils where you shoot stuff in it and you see some scattering pattern behind the gold foil. But this had a problem in classical description because, circulating electrons, they emit radiation, they lose energy, and then they just collapse into the nucleus and we would be dead. Yeah. So the universe would be literally dead because nothing is there. All energy is somehow gone. Now, Bohr, at the time, he used the same model in a sense, but just said, Planck and Einstein told us that energy is quantized. So there must be some minimal amount of energy where the electron then cannot fall into the nucleus because he cannot get rid of it. That was the basic idea. Yeah. And that he used in a phenomenological description to describe this Balmer series. So he said, the energy that the electron around the nucleus has is quantized. That means we have some certain niveaus, we call it now, and going from one niveau to the other, which they called electron jumps, I think. There were also people who said, that's huge bullshit. How can this electron jump? No, but this going the electron from here to there gives you exactly the emission lines, right? Now, then came de Broglie with the de Broglie wavelength. And the motivation for this de Broglie wavelength was the atom. So he said, if we give the electron a wavelength through this formula, then the allowed orbits around the nucleus are exactly the standing waves that fit to this wavelength. So he had an explanation for that there are these, what we now call quantized levels. In the end, it failed. Yeah, it cannot describe the whole thing, but the idea was there with this wavelength, and it led to many other experiments that in the end supported this de Broglie wavelength, but for the atom, it just failed. Yeah, and then came de Broglie was when 1922, 3, 4. I forgot. It was during his PhD, and then came this golden area of quantum mechanics. That was the area between 1925 and 1928, where basically everything that we know now was developed. Yeah, there was Schrödinger, Heisenberg, Dirac, Wien, Pauli, all these names that we know now, they worked exactly in this period. Bohr, Born, and so on, Ehrenfest. So that were these these big names now, they all gathered also in the Solvay conferences that some people might have heard of, where these things were discussed. And then there was a rapid development in these 2-3 years. Yeah, that was then the birth of this modern description, also the mathematical description of these effects. Until that point, I think until De Broglie, everything was more like try and error. Let's try some simple formulas. Let's try some, wavelength arguments. Let's try this. Let's try that. See if it works, how far it works. But there was not this general framework how to deal with a problem in general in quantum mechanics. And this was the huge revolution done then by Heisenberg and Schrödinger. Yeah, with the foundations of the mechanics in quantum mechanics. Yeah.
So in quantum mechanics, there's also this concept of superposition of states. And there's this famous example of the Schrödinger's cat. Mm-hmm. And could you elaborate a bit on that?
Okay, Schrödinger's cat. This is of course, it's a Gedankenexperiment, because everybody knows a cat and everybody knows that it's not dead and alive at the same time. But the Gedankenexperiment is the following, that you have a cat in a box, and if you put it in a box, at that point it's alive. And then you put next to the cat a poison and some statistical clock, so to say, either a radioactive decay material, whatever. But it gives you a probability of, let's say, 50% that something happens with this thing. It emits the poison and the cat dies, but with a probability of 50%. Yeah. So that would be a classical explanation, so to say. Now in quantum mechanics, we said already that it's a probabilistic theory. In quantum mechanics, we would describe the system, as you correctly said, a superposition of the two probabilities, of the two possibilities, of the two possible outcomes. And in that sense, you could say, yes, the cat is alive and dead at the same time, because the weight of these two states in the global state is the same. Yeah. So there's no preference for cat being dead or cat being alive. Now, at the moment where you open the box, you look at the cat and then it's dead or alive, obviously. Yeah. So that brought people to this paradoxon that we, as a spectator, or as somebody,
macroscopic also spectators in a sense.
Yes. Yeah. So as a macroscopic spectator can influence this. Just if we look 10 seconds later, maybe the outcome would be different. These kind of things which are very odd. Yeah. It is about, this goes back very far to philosophy about realism. Yeah. Or this anthroposophic point of view that does something happen if we don't see it? Like, does a tree make a sound if nobody is in the wood to hear it? These kind of things. And if you put it into quantum mechanics, that's the problem. Yeah. But it's a Gedankenexperiment that you can even resolve. Yeah. You just need to accept the mathematical treatment, which is a complicated thing to do. Yes. But if you accept that the treatment is the treatment of states, so we are in specific states, which is to be defined what it is, and then the measurement does something to the state, then it's what it is. And there's one thing that helps a lot in all these discussions, that if you think not of single boxes, let's think of millions of boxes. Yeah. So millions of boxes with cats, millions of boxes with poison. Okay, you won't do it in real life, but the idea is then if you open all of them, half of the cats will be dead and half of the cats will be alive. That gives a statistic meaning to these probabilities. Yeah. And in that sense, one can get a better idea of what probabilistic treatment means. The point is, quantum mechanics for macroscopic objects is not the theory that you want to apply, right? I said in the introduction that quantum mechanics is a theory for small objects, small timescales, microscopic things.
So, as you in the end now also mentioned, if one would really construct this setup, it would not work, right? This Schrodinger's cat, if you would reality build this and try this setup, it would not.
No, sure, it works. You can build a box, you can put a cat inside and kill it. I mean,
yes.
just to be clear, we don't want to kill cats.
Yes, no. We like cat movies on the internet.
Yeah.
No,
but the cat would not really be in the superposition of being alive and dead because it's a macroscopic system and there would be some interaction with the environment.
The point, so if you take a physicist's point of view, it doesn't matter. That's the problem. And as long as you don't look at it, it doesn't matter. It's then a question what you make out of it after you look at it, so to say. Do you then say, it was in a superposition state? For the Schrodinger's cat, it's a simple problem. Yeah? It was in a superposition state, and now when I look at it, I let the wave function collapse. That's the term that we use. And then it collapses in one of the two possibilities, and I killed the cat, maybe, yeah. But that's just the mathematical treatment of it.
Yeah, so what I mean is, it's a nice way of getting an intuition for how things happen on the macroscopic level. But for macroscopic systems, we don't observe these type of things, right? So why does quantum mechanics apply so amazingly to microscopic system, but still we cannot observe it in our macroscopic world?
Mm-hmm. Okay. I think one explanation that one can give is related to this de Broglie wavelength also. The de Broglie wavelength gives you, if you want to call it like that, an length scale of the object that you're interested in, yeah? And you can calculate this because there's a formula for it. And if you do this for an electron, this length scale is some nanometers. I forgot the exact values, but it's something small, but still reachable, yeah? What is the result of this is that this wave-like character of electrons, that's another thing that's very complicated and difficult to understand for people. The wave-like character of this particle can be seen. And the first experiment was also in the 20s. It was the electron diffraction, right? You shoot electrons on a material and then you see diffraction patterns that you would calculate from if a water wave hits some obstacles.
Which means with maxima and minima. So
with maxima and minima, with interference, deconstructive, constructive interference patterns as it would be a wave. Yeah, that was the diffraction experiment. And then only later, I think it was in the 60s, came the double slit experiment, which is a similar realization of the wave-like character of the electron. But it's this wavelength that is decisive. Now, there was a spectacular experiment just recently at Technical University Vienna by a group from the Atom Institute. They did the double slit experiment with neutrons. Now, I can explain quickly what the double slit experiment is. It is, you have two slits, so a double slit, and you just let the particles flow in towards this double slit. You let them go through in whatever form, we will talk about that. And then you record after this double slit on a screen what happens. When do the particles arrive? Where do they arrive? Do they form a pattern? Yes or no?
So we record in like the bright spots on this.
The bright spots. So you have a CCD camera. Mm-hmm. So there are electrons. Okay, with electrons you do something else, but for photons you would use a CCT. For electrons you do an electron counting measurement. Anyways, the particles go through and then you measure where they hit the screen. If you do this for water waves, it's simple. You have two slits, you have wave fronts, interference, and so on. Now, the funny thing is, the same happens for electrons. Yeah, for electrons, you see an interference pattern as you do in the diffraction experiments, and the length scale of the double slit needs to be around the de Broglie wavelength. Yeah, that's why it took some time to really produce this experiment, because still it's nanometers or even shorter, so you need to make slits of this size, so it's not so easy, but you can do it. And then the nice thing is, in many, many experiments, then many, many years later, people started to just shoot single electrons to the double slit. Yeah. So a single electron, and if you think naively, it would go to one of the slits and then hit the screen. And the next electron goes to other slit, and then it's some statistical distribution. Now, if you think about statistical distributions, you would not see an interference pattern because there's only one electron going through one slit. No.
So it's either this one bright spot or the other bright spot.
It's the one or the other. Now, if you start recording the pattern with the single electron experiments, you start seeing spots here and there, and you have to record it for a long time. But at the very end, you see an interference pattern that is coming from a wave-like character of the particle. So the only explanation that you can give seriously is that the electron went through both slits at the same time, somehow. So it split up into a wave. It knows about where is the other slit, how long is the distance, what is my wavelength, where should I interfere destructively or constructively. Yeah? And the guys in Vienna did the same thing now for neutrons. Now, you might think, okay, electron, neutron, proton, it's all elementary particles, it's the same. No, electron is much, much lighter. An electron has a mass of 10 to the minus 31 or something, and the neutron is orders of magnitude heavier. Now that means that the wavelength is orders of magnitude smaller. And still these guys could measure these interference patterns for this. It's not a macroscopic object, but it's a bigger object. Yeah? And you can go even up to molecules and see interference patterns. Yeah? Now, if you push that further and you take...
We cannot shoot humans, right?
We can not shoot humans through a double slit. No, that doesn't work. We can even not shoot soccer balls through double slits. So the problem is that the relevant length scales that where these quantum mechanical phenomena show up are so small that they are, let's call it, beyond any resolution that we can tackle with any machine that we have. Yeah? So it's just not measurable. It's nothing that is relevant due to the scales that you need to face.
So what you're saying is the larger the size of the macroscopic object that you want to infer the wavelength of, and then the smaller the wavelength will be, like in the end, eventually like beyond resolution. So like
or put it differently. For the electron, you shoot the electron into it's a double slit or an array of slit. It doesn't matter, but the building size of the double slit is much larger as the electron is. Yeah, it's like we go through a door, kind of. Yeah. Now, if we make ourselves bigger and heavier, the door gets smaller. Yeah, and at some point we don't fit through the door. That's the point. And this can be radical. Yeah, like the door is 10 orders of magnitude smaller than I am. So how can I go through? It's a bit decisive because we talk about our particle-like nature, right? So one has to be careful not to mix this up too much. But there is a limit to that. Yeah, and this is where microscopic and macroscopic objects then are different. And we use another theory for macroscopic objects, which is classical mechanics or hydrodynamics. They're there for everyday life for macroscopic objects, right?
I'd have a follow-up question about what you said, the postulates, if you want, of quantum mechanics, because you said before one has to accept something and then like to build on top of that. For example, quantum mechanics has in the name the discreteness of nature, it seems. So like for an external listener, observer, it seems like, okay, if I hear quantum mechanics, I think everything must be quantized. But I mean, we know that quantized solutions are actually solutions of the wave equations for bound states as opposed to free particles. Because, for example, if you have a free particle, you can have a continuum spectrum of energy, as you said before. So like, also, this duality, I think, is important to mention, because otherwise it seems that quantum mechanics is all about like having this discreteness and then like one forgets about...
You're right. Quantum mechanics just allows for discreteness. Let's put it that way.
But it's not a postulate, so...
It's not a postulate. There are other postulates, but that everything is discrete is not a postulate of quantum mechanics. Yeah. It even helps because you can apply quantum mechanics in situations where you don't have quantized spectra and it still works. Right? So it just allows for quantized phenomena when they are real and when they're relevant. Yeah. The point is, maybe coming back to Einstein and this question about reality of the thing and, is this real or is this just a mathematical construction? Einstein, as I said before, he never believed that this is real. He believed in the math and he said, okay, it's fine. We get some probabilities for experiments. But he said there is something behind. Yeah, there's something hidden. And that was this famous theory of hidden variables. Yeah. So that's a way out, so to say, for the non-believers, let's call them non-believers, that quantum mechanics is just an effective theory, which is what it is, but there's something behind, and this something behind is the more general theory. So what is the problem? The problem is coming from these probabilities, yeah? So quantum mechanics, as I said, is probabilistic. That means we don't get deterministic answers that we were used to before. If you use classical mechanics, you have a particle, you've let it fall down. Newton's mechanics tells you when the particle is where exactly, to highest precision, if you want. Now, quantum mechanics does not do that. Quantum mechanics tells us that the particle is with a certain probability at that point at some time, but it doesn't give us this deterministic point of view. And Einstein said, this is not intrinsic, but the problem is insufficient knowledge. That was how he called it. And he said there must be some hidden variables that describe this ignorance. And if we know the hidden variables, the ignorance and probabilistic nature is gone. That was the statement. Now, you can put this even to a test. And this is this famous Bell's inequality. Yeah. So Bell in the 60s or 70s or 50s, I don't know, it was at some point after the war. He came up with an inequality without going into the details, but the inequality lets you decide if a measurement is in accordance with a hidden variable theory or with a probabilistic theory, in simple terms. The experiment is notoriously difficult because you have to get rid of all kinds of external influences and so on. But in the end, Alain Aspect managed to do this experiment, and he could show without doubt that nature is probabilistic. Yeah. So this original postulate that we have to describe these things with probabilities and not with trajectories, that was much, much, much later on just experiment said it's true. Yeah. So it was not a matter of belief anymore. At the time of Einstein, it was belief. But now we know that this probabilistic nature is really the description of these elementary particles. It's not because we don't know better. It's the same thing with the uncertainty relation, right? So Heisenberg, he even did not formulate it mathematically, although it's called the Heisenberg uncertainty principle, but he just wrote it down in sentences that he thinks that in the very precise example, the position and momentum of a particle cannot be measured at the same time. And this is not a problem of the measurement, how you set up your tools and your machines and so on.
I mean, as accurately as one wants to.
Yes.
Because you can
if you think of
measure
mechanics, it's a problem to measure position and speed at the same time, because speed needs two measurements, position one, and so on. So, but you can solve this in a technological way, yeah. But quantum mechanics says, no, there's something fundamental that this cannot be done at the same time. The mathematical formulation then came later, so Heisenberg didn't do that himself. But then it went into the mathematical description, yeah. And now we use operators and commutators and all this crazy stuff that you have to learn during your studies. And this is then a postulate, but it describes nature, right? And in physics still, we are at the position that we accept the theory unless experiments prove us wrong, in a sense. That happened over millennia, yeah, always. So we accept the theory, use it, we apply it until there's something popping up that doesn't work, as it was with the blackbody radiation. And we know now that there are certain things that also don't really go in line with quantum mechanics, which is relativity. That's one of the unsolved problems, to put gravitation and quantum mechanics into one framework. But there are many problems where this is not relevant, so we can use just quantum mechanics for that, yeah. It's proven by success, if you want.
Quantum mechanics also has a very philosophical aspect, I think, because you mentioned a few times this collapse of the wave function. But what exactly does this mean?
That's a good question. I don't know if anybody has a very good answer to that. Philosophers have answers to that, but they're most of the time not written down in a mathematical form, how to grasp it. So if you want to put it mathematically, the collapse of the wave function, you can describe. The collapse of the wave function is it was invented also in Copenhagen by Niels Bohr, actually. That was this Copenhagen interpretation, yeah, that the wave function is a general wave function. And if you do a measurement as you do with the Schrödinger cat example. In the moment where you look at it, the wave function collapses into one of the possibilities. Yeah? So that was this idea. And there was one thing in the Copenhagen definition. The spectator is out of the game, so to say. The spectator is a macroscopic object and it's not described in quantum mechanics originally. So people forgot about this. But in the original interpretation, the spectator really had the role of I decide now. Yeah? You can put this spectator or the measurement machine or whatever it is into the quantum mechanical description, and then the collapse of the wave function follows naturally from how to describe the measurement process. Yeah, so the machine can go into a state, but that means also the system under investigation has to go into a state at the same time, although you don't collapse the total wave function of the universe, if so want. Yeah, so this collapse of the wave function it was invented to take the spectator out of the game, yeah. But if you take it in, the quantum mechanical description is not so complicated, yeah. It's then related to density matrices and reduced density matrices. So that's the mathematical point. But it's possible. Again, if you don't go deep into the math, it sounds very strange. Now, if you go into the math and you accept that this treatment makes sense, it's a natural follow-up of your equations, yeah. I forgot who this scientist was, but there's a famous saying that I think it was attributed to Feynman, but I think it's not true that he was it. That he was also bombarded with questions from students about, what should all this mean? And I have no interpretation for that. And I said, shut up, sit down and calculate. Right? So you can apply the formulas, you get numbers out, you can relate the numbers to experimental data, and then you see if it works or not. So if you're not bothered by the philosophical implications, you can live without thinking of them too deeply, yeah, and just apply the theory and in a most successful way. But you're right, philosophers like this. Yeah, there are brilliant people working in this, let's say, combination of physics or science in general and philosophy. Most of the time, that is my experience, in areas where the experimental verification is difficult, right? Because that's the realm where you can play around these games, like what is really the universe, what is the truth. If we talk about the resistivity of a material, there's no question about what is the final truth, because I can go to the lab and measure the resistivity. And then I know what it is. Now I can talk about what is the origin of this, yeah, but it's a very concrete example. Yeah? But the question about how large dimensional is our universe, is it 3-dimensional, 4-dimensional, 10-dimensional, and it's just, we see it effectively in the way we see it because it's the energy scale that we live in, and these kind of things. Of course, you can make a lot of questions about it. You can spend millions of pages writing on that. The problem is putting that to a test. For instance, we went into this superposition, right? And you might know that Zeilinger got the Nobel Prize in Physics for exactly these kind of problems. Yeah, he took 2 photons and he superposed it into a so-called entangled state. And that has been put then to very far distance. Yeah, so 1 photon here, the second photon there, and it can be millions of kilometers distance. Yeah, and then the experiment is the following: you measure a property of the 1 photon, and that, since now the wave function collapses again in that language, the wave function collapses, and that also locks the properties of the other photon, which is millions of kilometers away, but it locks it instantaneously. Yeah. That was also a huge problem for Einstein that led to this Einstein-Podolsky-Rosen paradoxon experiment, this very famous paper from the beginning of the 20th century. Yeah,
because the problem was that the information can travel at most at the speed of light, right?
Yes.
So you cannot have an instantaneous transfer of information.
Exactly. So Einstein, in his very famous work on special relativity, he postulated, again, that the speed of light is the maximum speed in the universe that energy information can travel. It's not the maximum speed of that you could see. It's just the maximum speed of energy and information. Now, this obviously violates this, because you can measure this one guy and instantaneously the other guy locks into some state. Now, if you think about this closer and deeper, you realize that this is not contradicting this maximum speed, because you need to get some information about the measurement on point A into point B to decide what needs to be done. So you need a classical channel in addition to harvest this thing. Yeah. So there is no problem with special relativity. But still at the time, Einstein thought, no, that's not possible. That's a paradoxon. Now Zeilinger did this, and still people think, oh, that's very fancy stuff. And then I was listening to a talk by, it was Christian Wütterich from University of Geneva. And he's a philosopher and physicist at the same time, and he's working on quantum gravity. So how to reconcile quantum mechanics and gravity. And then he said, it might happen, we don't know, but it might happen that all these paradoxa that we now construct with this entanglement, because we call that paradoxa, that might just be resolved in a quantum gravity theory. Because the problem also with this entanglement is about, we are talking about questions related to distance, and how far are things apart, and how far are things apart in time. So equal time means they happen at the equal time, but we know from special relativity that equal time is not a concept that is useful, because equal time at different points in space has no meaning, right? So, or one has to give it a meaning through special relativity and Lorentz transformations and so on. So what happens if our space is a bit more complicated, and in a more general description, these 2 points of space where these photons go, they do never separate in our high-dimensional space-time, but it's always at the same local position in space and time, maybe. And it just looks like this very complicated thing because we look at it with our eyes in 3+1 dimension. You know, this is a thing we cannot judge now because it has to be proven or disproven at some point by some experimental verification, but we should never forget that also our paradoxa might be resolved in a very simple way at the very end. And in 20 years, people say, how could these guys there think that this is working like that? So we will see what the future will bring, because quantum mechanics is now 100 and let's say it's 100 years old, almost exactly. If you take de Broglie and Schrödinger, it was 1925. So next year we have 100 years of quantum mechanics.
Happy birthday.
Happy birthday. And the development was quick. So I'm not brave enough to judge what will be now in 100 years. Yeah. So if you think all the developments that we have seen since the First World War, which is roughly the time span, it's amazing. And the speed is even increasing. So we should be careful of overjudging what we are doing right now. And
so just shut up and calculate.
Just shut up and calculate and be humble, yeah? And don't overestimate what you do for the future of humanity, right? It's always, things will prove you wrong or will prove you right. We will see.
Okay, thank you, Markus, for your time.
Thank you for having me, and thanks for listening to me.
So, thanks for listening.
And hear you next time.